Good afternoon. Today's topic is heterocyclic rearrangements. Okay, it's a kind of topic not covered in one single heading, and I had to collect from different places the different rearrangement reactions. Of course, all of us know rearrangement means basically the molecular rearrangements. These molecular skeletons undergo rearrangements, and in my list there are about 10 different rearrangements, but today I will be only covering 7 rearrangements. 7 rearrangements. Well, out of the 7, probably the first one has already been talked in one of the earlier classes. If you remember, that was the reaction called Alprazolam reaction, right? Alprazolam reactions, and what is it? It's a Alprazolam rearrangement, right? And it's a reaction of hydroxy alkyl furan derivatives, furans 2 what 3 pyranones, right? 3 pyranones, and actually it is 6 hydroxy 3 pyranones, 3 hydroxy 3 pyranones. If you see, if you try to recall, it is something like this. It will have a hydroxy at the side chain at the 2 positions. Then you have to do, mind it, it is an oxidative kind of a reagent, either metachloroperbenzoic acid or tertiary butyl hydroperoxide or NBS methanol, all these things. Eventually what you will be getting? You will be getting 3 pyranones, means oxygen with respect to this is carbonyl. Then, and easy to remember though, but easy to remember. Then you have an alpha beta unsaturated system, and the final one is occupied by this. Today we will be talking about a very similar reaction. This is known as Pian-Catterley rearrangement. Pian-Catterley rearrangement is very similar to the Alprazolam reactions. We will see, maybe we can write here. It is something like this, quite similar though, quite similar. And let us say if you have R up here, and under the presence of acid, dilute acid of course, dilute acid gas. Anybody knows what is the product? The product is a cyclopentene derivative. It is a cyclopentene derivative, and this R group is at 3 position, and then OH group at 4 position. OH group at 4 position. This is 4 hydroxy cyclopentanone. It's 2 different contrasting reactions though, but if you see here, the structure is very similar to the previous one, but in this case I think this should be methyl group here. This should be methyl group here in the Alprazolam reaction. Okay, and the third one I will talk about, quite famous. This is known as Dimroth rearrangement. Dimroth rearrangement. That I will talk about. Then this is a very pretty interesting reaction. Again, Korn 4th rearrangements. I have named it Korn 4th and Reeves, because Reeves has contributed quite a bit of chemistry to these rearrangements. Then there is a pretty simple chemistry called Steglich rearrangement. Steglich rearrangement. And probably I will stop this one. Okay, then probably will I think we will stop probably here. One more reagent called Boeckel-Hyde, and so Boeckel-Hyde rearrangement, and which also is pretty similar to Poronovsky reagent, and basically it deals with the rearrangements of rearrangement of aromatic N oxides, aromatic N oxides. Okay. And under this category, then there are other things like Gabriel-Coleman rearrangement, many of you probably, and then Ferrier rearrangements. Then those are not really directly related to the heterocyclic chemistry. In principle, if you have studied any rearrangement in the carbocyclic chemistry, that can be applied to the heterocyclic chemistry. I am not considering those. Let us say Claisen rearrangement. If you just do Claisen rearrangement on a heterocyclic nucleus, you will end up in a heterocyclic molecule. I am not talking about that. Let us say 2,3-Wittig reactions, 2,3-Wittig rearrangement. Those are the reactions known for the aliphatic systems or non-heterocyclic systems. So, in any case, we will look at this since Achmatovic has been covered before. So, let us take Pian-Catley reaction. Pian-Catley already we have told about this. Pian-Catley is already been told. So, what we have to find out? We have to find out the reaction mechanism. Okay. The starting material is this hydroxy alkyl furan, and the reagent also you have to remember it is just a dilute acid, and so I am just rewriting. So, it is a cyclopentanone and R, and then this hydroxy here. By the way, you have to take care of this stereochemistry. The stereochemistry is now sorry, mistake, right? This is wait a minute. It should be okay. I think it should be hydroxy here and R, or this mistake. I think that somewhere we have made a mistake. We will go. We'll see. We'll see this once we see this mechanism. Probably I think it would be clear. Apparently, R is here and this hydroxy is here. So, 4 hydroxy. 1, 2, 3, 4 hydroxy, 5 alkyl. Mind it, the stereochemistry here is trans to each other. I think we are right. Let us see the look at this mechanism. What is the possible mechanism in the presence of acidic water? So, OH would be added to this one. Then because of the presence of water, this loss of water would dearomatize the system, and what we will get this hemiacetal kind of thing, right? Hemiacetal, and then in the again further, all of us know hemiacetal breaks open, and what we will be getting? We will be getting an oxonium ion and double bond here. Then you can say this is oxygen, and this oxygens of course would be protonated, and so then you will have this R here. Okay. And mind it, this is it's pretty similar though. It is you will see here you have carbonyl double bond, and this is what? This is again a this is carbonyl here, right? Okay, I think what I will do here. Okay, let me just rewrite this oxygen hydrogen plus and a double bond up here, and you can rewrite this way. This is R, and this is right. This second carbon is oxygen, and this, right. Okay, so again this could be rewritten as OH and then this, and the positive charge is now smeared with this one. Now, what is it? It is a 4 electron cationic system. 4 electron cationic system means you would expect a reaction, a name reaction. What is it? 4 pi electron system, and it is a cyclization process. So, 4 pi electron cyclization thermally, what is it's conrotatory or disrotatory? Conrotatory. So, conrotatory means if you have two groups like this, then it will be trans to each other, and that's the reason this hydroxy and this one would be this R here, this OH, this should be R, this should be OH, it's trans, right. The other one, of course, is if you just do the electron balancing, it would be an alpha beta unsaturated ketone, okay. And what is the name of the reactions? Anybody remembers? It's a pretty well known reaction though. 4 pi electron cationic system cyclizations leading to cyclopentanone. Yes, right. So, it is basically a Nazarov reaction, So, let me say from the furan you are going to get this, that means you have to make a small corrections here, the correction should be R should be here, right, R should be in the 5 position. Okay. So, these reactions has been extended to many systems. For example, very recently in 2010 same reactions has been carried out with the substrate of with the methyl group at the side chain and hydroxy at the side chain, and this without water. So, you are basically using an amine, and then in the example particularly one which is this then dysprosium is dy, I guess, is a triplet. So, it is a non-aqueous medium. So, what you will be getting, so you can just blindly write the cyclopentanone, and R in this case is a methyl, and the disposition is trans. Now, in the place of OH, so you can expect an amine. So, this was done, that means what we can say is an Pian catalytic rearrangements. So, like this, I mean there are other examples. You can do also the intramolecular version, and if you have an inbuilt OH group there, instead of this water adding to this carbocation, one can expect an addition of this. Okay. And I think I will not talk much about the other examples here. Let us look at the one more important reactions, that's pretty famous reactions in heterocyclic chemistry, that is Dimroth. That is Dimroth rearrangement. Dimroth rearrangement, what is it? It is basically amine substituted. So, you can say amino heterocycles getting converted to amino heterocycles. For example, I think if you take an amino pyrimidine here, aminopyrimidine, then you treat this with ethyl iodide. Of course, it is very difficult to out of the 3 nitrogens, it is very difficult to point out which one is more nucleophilic in nature, right. This more nucleophilic in nature, which one you think? and okay, between the two pyrimidine nitrogens, both the nitrogens of pyrimidines are equivalent, right. So, that means the only competition between either of this ring nitrogen or the external nitrogens. In most cases the ring nitrogen is because electron is pulled towards the aromatic ring system. Okay. So, this reaction would give you this initially this N-ethyl derivative, then it tautomerizes to corresponding imine and this. So, basically this aminopyrimidine. Then if you treat this with sodium hydroxide or hydroxide, you will end up in the dislocation, or I should say translocations of the nitrogen. So, eventually we will be getting NH and ethyl group here, NH and ethyl group here. So, compare basically what is this Dimroth rearrangement? Dimroth rearrangement is this A getting converted to B, A getting converted, this is basically the Dimroth rearrangement. What is the change you see here, that this ethyl group is located at this ring nitrogen, now it is relocated into the side chain nitrogen. So, that means in almost all of these Dimroth rearrangements, eventual product is the amine with the alkyl side chains or whatever the side chains are available, that would be finally be located into the side chains. Okay. And what is the mechanism? This mechanism wise, if you think about this in the presence of water, so it would be basically water adding to this nitrogen here, I guess, or let us say nitrogen, then you will have double bond NH, and this is NH here, and then this basically just 1 for water addition, 1 for water addition. Then what happens in the presence of this base again, this undergoes ring cleavage. So, you will be getting this you can say in fact did I make any mistake? Oh, okay. I think instead of writing this, I think you can just it would be easier if you just break open here. So, you will have aldehyde, the double bond, then nitrogen and this, and then imine form, and this is now NH and ethyl here, ethyl here. So, this is I mean if you just okay, this is equivalent to this aldehyde double bond NH, and then just basically rotate this terminus. So, it will be NH ethyl here, and this is now imine, right. And then as usual the driving force is again just what you will be getting, you will be getting again very similar to one of these previous intermediates, and so this should be NH and NH here and the double bond, right, and just the reverse kind of thing. So, reverse kind of thing, and then if you can think of, right, loss of water. So, the product would be the say pyrimidine of course, and now the side chain is ethylated. So, initially the ethyl group was placed at the ring nitrogen, now at the side chain. So, what is the summary? What is the main features of these Dimroth rearrangements? Basically ring opening and the recyclization. This is a common actually phenomena in heterocyclic chemistry, common phenomenon in heterocyclic chemistry. whenever there is a possibility, it will move towards the most thermodynamic or more thermodynamic product. Okay. Let me take you to one more example. Also, it is true for, I think it is true for 5-membered ring. I think I will not give you the examples. Let us say maybe we can take care of 5-membered ring first. Okay. If you have a triazole, and see here is a phenyl. Now, the side chain you have a free amine and then R. Now, in the presence of even just dissolving in pyridine, you can expect a reaction. So, what is the possible reaction here? There is, in the previous case it was the alkali, right. In this case there is no driving force, just basically the polar solvent. So, it assumed to be in equilibrium with a deuter ion of this dipolar ion of this kind. So, nitrogen is mean here NH N minus pyridine, and which is equivalent, sorry, this is NH2, this is equivalent to that means just rotate this NH2 here, nitrogen plus, and now this is what? This is N and pH, right, NPH, and then all of you can understand that this nitrogen, this proton can undergo internal transfer, making this nitrogen NH or this nitrogen negative. So, it can be in equilibrium with. So, these are all simple mechanism. So, you can think about this NHPH here and then recyclages. So, recyclages. So, even that means you are starting from a heterocycle triazole, you are again ending up with a heterocycle which is triazole, and the other side chain now is pH. So, ring opening, ring closing. So, these are all there are other examples in more complicated cases. So, but the essence is same, that you just if you have a driving force for the ring opening, you can get to this. For just let me just mention one more very similar kind of rearrangement. It is not exactly the Dimroth rearrangement. For example, if you are to make, let us say, compound of this kind, cyclohexanone and 2 alpha cyanoketone, how do you make it? There are so many, I mean there are so many ways to make. If you try to, let us say, do a chlorination here, bromination here, then displace cyanide, no, that is not a very simple straightforward process though, because all of us know cyanides will form cyanohydrins. Okay. There are other complications. Cyanide also can induce the elimination process. So, one of these ways to overcome this sort of thing is to make a compound of this from the corresponding oxime, right. If you have an oxime here, you can cyclize to the corresponding what, oxazole, isoxazole. Now, if you treat this with a strong base, see, it's unlike a strong base, it just opens up. That means a base would pick up this proton here and it will clip the isoxazole ring systems to corresponding. This is just what I am saying, it is not a ring closure, just ring opening reactions, and this is only specifically meant for the isoxazole cases. Okay. And let us now go to another very interesting rearrangements, that is known as Cornforth. Many of you have heard of this name right before. Cornforth, no? Cornforth is a Nobel laureate. Nobel laureate, he exclusively worked on biosynthesis, also he worked on synthesis, and but in this case I will also give the credit to one more young scientist called Reeves. He has contributed quite a bit to this Cornforth rearrangement. What is it? It's there are two kinds of the rearrangements. Okay, there are two kinds. One is thermal thermal, the other is base catalyzed, actually base catalyzed reactions. Thermal one again it involves only the oxazoles, and with a substituent at 4 and 5 positions. Let us say if it is an R1, R2 and R3, you see here just heat, or even MW, right, MW. So, what it is, anybody knows? Microwave. So, what we will see here, there is a big change, noticeable change rather. What do you see? You see 1, 2, 3, that means there is an interchange of the alkyl group here or some groups here. Okay. Let me tell you the specific example. I think that would again you draw an oxazole system, and see this is immaterial almost. So, I will write phenyl here, do this heating, and what do you expect? That means this ring skeleton is unchanged, this portion is unchanged, then 2 position is unchanged. So, 1, 2, 3, 4 and 5 undergoes changes, and in this case what you will expect? You will expect OIT here and NH2. That means the position of NH2 and OH NH interchanged. And let me take take you to another example. Let us say I will not, okay, you just take this one. Now, this NH2 is replaced by aziridine and the OIT remains OIT, and if you do this once again, it is a very simple reaction apparently, and what you will see, there are other examples. You will see this OIT here, and this is nitrogen, and this aziridine group here. Okay. So, given this, I will give you a problem, and you will see, and let us see if you can give this answer. Here again, I think this is phenyl again. Okay. Take oxazole again, and then you have to have you do not have to have 3 substituents, but I am putting one more substituent. There are so many examples, and if you take aldehyde and here nitrogen. So, previously oxygen and nitrogen basically they interchange their places, right. Now, in this case you have aldehyde and this azide. So, what do you expect? Well, without much thinking, you can just simply write the skeleton first. This 2 position side chain is untouched. So, now you have to do these manipulations. If you just carefully look at, so just tell me what you have to do. So, what are the common structural features that is required? You have to have a carbonyl at the 4 position, that is important, carbonyl at the 4 position, and that remains unchanged. So, obviously then what should I write here? Hydrogen, that is it. So, hydrogen, and here you will see this azide. So, basically acyl azide, and okay. So, what is the mechanism? What is the mechanism? Let us look at the mechanism. There are plenty of examples of this kind. Mechanistically, let us see oxazole, right, phenyl, and you have to have a carbonyl here. Let us say take one of those examples, maybe NH2 is perfect all right, and this was OAT, right. What is the driving force and how do you go about the mechanism? I have given you the clue before. In most of the heterocyclic cases, what is the mechanism? Ring opens and ring closes. So, but you have to just identify the right driving force. What is the driving force here? In some cases, all these ring opening, ring closing, they are triggered by either proton or OH minus, okay, or thermal. If it is a thermal, then of course there is no handle of protons or OH minus. So, possibly this would be the cleavage driving force. That means pH C, right, nitrogen here, this plus, and minus OIT, and what it is, right, this is okay. And then of course, when you have this, you can also think about, right, also think about pH C triple bond, this one, right, oxygen minus this OAT, right. So, you can reorient, then you can reorient the way we write. I think better it would be better if you write this way. Nitrogen, and then double bond here, this is oxygen minus NH2, and this is now CO OET, and this is pH, and just a reverse of the process, and so if you do so well, you can end up with the right, you can come up with the right product. And so, this would be now OAT, this is NH2 and this. Okay. So, for the mechanistic purpose, this is perfectly all right, right, but you have to identify the driving force. When I say overall driving force, they are isomer, in nature, then why it is changing from one to the other? Any idea? Any guess? There, see, if you start with the final starting material, this final product, both are identical structurally, I should say formula wise isomer, they are isomeric in nature. Then why should one to transfer to the other? Obviously, without saying without any analysis, you can say that this must be more stable. Why it is more stable? That is, or rather I should say the starting material is unstable. Why it is unstable? So, that is what I have to find out. Actually, I have many more examples, and from the examples what I studied, it appears that the oxygen, the two positions should have a group that is less electronegative than the previous one or starting material. Let us say if in the previous case you had what, oxygen here more electronegative. So, this one has to be less electronegative. I mean, one can invoke any kind of explanation as if two dipoles, like two big trees cannot grow together, right. That is a common saying. Okay. That means I mean two big tree will never grow together, either one would be shorter, other would be bigger. Okay. And then one more base catalyzed reaction is known, also again discovered by Conforth, very similar substrate here, very similar substrate. And if you treat this with sodium hydroxide and of course, it is heated, in this case it ring opens, and ring opens, and the ring opening this was discovered in 1949, and the product that is formed is CHO here, so malonaldehyde, basically you get the dialdehyde and NH and pH. Okay. What is the mechanism? Mechanism wise again OI now alpha beta unsaturated aldehyde. So, probably this undergoes Michael addition, then it kicks out this alkoxy. So, you will have nitrogen, oxygen minus, then okay, CHO, and then after all these proton transport automerizations you can get this one. This was the original discovery. Okay. This was original discovery by Cornforth. Now, what Reeves did, he did a small trick here. It is a pretty interesting reaction. He took let us say, that means if you want to, for example, extend this reaction to something else, what do you do? This reaction has been known for, let us say, for oxazoles. Now, you are given a project or you have to formulate a project on this. What can you do? You cannot change this oxazole part because that is responsible for opening. Okay. You need an aldehyde, because that actually activates this molecule towards this ring cleavage. So, that means this part cannot be changed. So, what can you do then to formulate a new project on this? You do not have many places to change, right. So, what Reeves did, he took a substrate of this kind. What is it? It has a relationship with the previous example. What is the difference between these two? Or difference, or I should say what is the analogy between the two? Okay. See, they are both are oxazoles, no problem. They are both are having the similar structure, only there is change in the fourth positions, but there is a striking similarity. Okay. If you see here, there is a carbonyl up here, there is a carbonyl up here, but between the ring and the carbonyl there is a group called which group? Vinyl group. So, what is known as, that means vinylogous, right, that is it, vinylogous. That means all the see all of us know vinylogous compounds electronically they are similar in reactivity. So, that means one would expect them, that under the conditions of sodium hydroxide. So, sodium hydroxide. So, what do you expect here? This again you will get this NH like the previous example, NH now here, then this one is now aldehyde, right. So, this should be equivalent to an aldehyde, and this is now double bond R1, and then rest remain as it is, that is it. The group remains as it is, only the ring opens up. This is equivalent to what? Formaldehyde, hydroxymethylene formaldehyde. So, this basically what you are getting, you are NH, C and formaldehyde. In fact, if you recall the previous example, this was you can say pH, NH, NH, this is pH, and this is aldehyde, and this is aldehyde. So, I mean this aldehyde. So, exactly that is what is happening here. So, only thing that this portion is this one. Then I think you should be able to tell us what is the product then. We have learned so much of heterocyclic chemistry. We are now almost towards the end of the course. We have 2 more lectures to do. Okay. And so, what is the product now? Let us say, okay, I will tell you, you will get a separate kind of heterocycles. Hints.
There should be a carbonyl.
Which one? Oh, right, this one. Okay, fine. Okay, right. This is a carbonyl, right. So that means this is a mistake, huh? Right. Good, very good, very good. This is carbonyl, right. Yes, this is carbonyl. Okay. So now let us. Huh? Not really though. Not really. See, all these heterocyclic syntheses, all the heterocyclic syntheses are based upon reactions of the carbonyls and amines, most or basically all of these carbonyl and something. So, what do you have here now? And you have to find out the relationship. I say 1, 2, 3, 4, 5. So, that means 1, 5 carbonyl means you will get nothing, right. 1, 5 carbonyl, where do you get? If you have in case of pyridine, to find out pyridine, but the nitrogen has to come. Okay. The other way, what is the other possibility? What is the other possibility? Simply cis base formation. Alkali is good enough, is strong enough to convert this amide. NaCO pH is basically amide. Amide is converted to amine. So, it is converted to amine, that means NH2 and this is CHO, then this R2 and R1, right. So, what? So, what? Then this nitrogen undergoes condensation. So, what you will get? Pyrrole, that is it. You will get the pyrrole and the remaining aldehyde would be at the 2 position, and this side would be R2, right, and the other one would be R1, that is it. So, that means you are getting a nice way of making this pyrrole. Okay. And this reaction has been extended to many important or rather complicated examples. Let me see whether I should talk about it or not, because they look very similar, only thing that they differ how to make this substrate. So, these homologous substrates are made by normally by these Wittig reactions or Wittig reaction. Okay. And in complicated cases you do this aldol type of reactions to get to these alpha beta unsaturated ketones. Okay. So, this is a very good reaction, and there are other examples. So, we skip them. In fact, you can also extend it to thiazole systems also, thiazoles. So, that was oxazoles, but also you can extend it to thiazoles. That also eventually, because thiazoles, when alkaline hydrolysis, it gives the corresponding aldehydes. So, you will get very similar compounds, very similar compounds. The other reaction or that is to be known, this is known as Steglich rearrangement. There is a reaction many of you know called Steglich reaction. Steglich reaction is different from Steglich rearrangement. Okay. What is Steglich reaction? Anybody knows? Right, very good. What is this? Okay. Those who do not know, it is an esterification reaction. It involves DCC. So, alcohol, carboxylic acid and DCC, that is basically the Steglich reaction. So, you get the ester formation. So, it is a very similar reaction again in terms of the substrate, because it starts with oxazole and a substituent at the middle of the 2 position, and then if you have let us say group here R, and the 2 position is now occupied by a sort of a carbonate group and R1. The original discovery was like this. It was treated with a reagent pretty well known in organic lab, DMAP. It is a little slightly more stronger base than the corresponding pyridine. Okay. And under the condition under the condition what you will be getting, you will expect to get, a migration of this acyl group or the ester group, migration of the ester group. So, and this is now as OR minus, and now this one is a carbonyl, this one is a carbonyl. That means basically this group, this circle group migrates to 1, 2, 3 position, 1, 3 migration, acyl migration. You can say 1, 3 mechanistically, 1, 3 acyl migration, acyl migration. And what do you get? You get a product which is oxazolone, of course, and what else? It has a nickname though. Anybody remembers what is the nickname? Ending with azlactone. Take this amino acid, do the benzylation, cyclize this, what you get is basically azlactose, but in this case it is substituted azlactone. And what is the striking feature of this starting product? Why this reaction is picked up? There must be some reason, right? So, what is the specialty about this outcome? What is the specialty about the outcome? Azlactone, that is fine, but slightly different from azlactone, but there is a striking difference between the normal azlactone and the product we see here. See, in synthetic chemistry especially, I can tell you, you have to identify the real challenge. What are the different challenges in a synthesis, that you have to identify. That means, let us say for esterification, for example, I mean this is a common reaction, you can do things, but there are certain cases it could be very difficult. So, I mean that means for any reaction it is quite general, but not general for all the substrates. So, you have to find out the challenges. Okay. In this case, what you are doing here, actually you are creating a new carbon here. What kind of carbon? Quaternary carbon. Quaternary carbons are difficult to make, reason being they are crowded. See, if you have a substitution, plain substitution, no problem, second substitution okay, third substitution you are in trouble. So, that means the formation of a quaternary carbon is challenging, and that is what you are bypassing here. Through a rearrangement you are coming up with a new quaternary center, fine. What is the next challenge? Okay, utility wise is pretty, I think you can see, right. What is the utility? What is the utility? Utility wise you can go to corresponding amino acid. You can just, if you just do the hydrolysis, you will go to the amino acid. Okay. You have hydrolyze here NH2 and this will come at this carboxylic acid. So, that is one of these ways. And the other possibility, that since you are doing a producing a chiral center, so you have to see whether you can have an acidic version. In fact, very recently someone has devised an interesting catalyst, again an oxazole here, and this so for Steglich rearrangements what you need like this, and then if you have R group here, I will just DMAP and then a catalyst, thiourea catalyst. I will just simply say thiourea catalyst, which is a chiral one. That is it. It is a chiral one. It is a chiral one, and eventually what you will be getting? You will be getting a chiral ester here, and this oxygen and this carbonyl, okay. And then this is a lactone, this is a different kind of ester. So, you can also do little bit of the chemoselective reductions. So, you can convert into the serine derivatives, all kinds of things, and the EE in the example that has been cited is more than 99%, more than 99%. Okay. So, let me say this is a pretty useful reaction, And let me just quickly I think end up this lecture by saying one another well known reaction which was known in 60s. I think many of you must have heard of the discovery of Librium, right. What is Librium? Discovery of Librium, I think discovery of Librium. This was discovered in 1955 by a person known as Sternberg. Why did I say? Because he discovered this compound at the age of 60, means at the time of retirement. When he was about to retire, he had to submit the samples. One of his co-authors rather co-workers found that one of these sample was not tested for the biological activities. So, it was submitted for testing, and that compound was found to be the very active. Active means psychoactive, means, or you can say tranquilizer. It can induce sleep. And what was the compound? The compound actually was Librium. It is nothing but the structure wise it looks like this. Right, 7 membered ring. 7 membered ring is NH, and this is methyl group here. Nitrogen 1, 2, 3, 4, 5, 6, 7, right. Nitrogen here, pH, and there is a chlorine here, and this nitrogen is having oxygen minus, this is plus, this is N oxide. So, this is actually known Librium. It was discovered in 1955, but Hoffman Larousseau marketed in 1960 in the name of, I think many of you know this Valium. Valium is nice. Now, recently what people do, or what the students use when they are in tension for exam, do you know? Oh, okay, I know the medical students what they take, because they know what sort of medicine they should take. They take Alprazolam. Alprazolam is, that means what is this class of molecule is known as Benzodiazepine. Azepine means 7 membered ring, right. You have 2 nitrogens, diazepines. You have a benzene nucleus, benzodiazepine. Actually Sternberg what he wanted to do, he made a compound of this kind, this one and this chlorine here. He wanted to displace this methylamine and just simple displacement reactions he wanted to do, which was to be NH and methyl group here, this nitrogen, this and this chlorine. But as usual, most organic reactions do not listen to us, okay. They go in their own way, and so eventually he got this one. Eventually I got this one. You can work out the mechanism. That means that direct this. See, if you look at this structure here, this is basically imine, and what is the, by the way, what is the skeleton of the, what is the name of the skeleton? Last class I talked about. So you have 2 nitrogen, 1,3 position, you have benzene ring. What is the name of the skeleton? We talked about the synthesis of sinolines, thalazine, we talked about quinoxaline, we talked about quinazolines. What is it? Quinazolines. So, quinazoline N oxide. So, there are 2 possibilities. Amine nitrogen could have displaced this, but it did not displace. So, obviously, what was it? So, it is sort of an like aldol type of condensations, right, 1-2 addition. 1-2 addition takes place. This nitrogen here and this plus and minus, and of course, again like two big trees cannot be side by side, two nitrogens are on side by side. So, they do not want to side by side, right. So, what they do, they are satisfied with breaking the ring, and so what you will be getting will be this oxime, and the other chlorine all of us know that will remain intact because it is an aromatic chlorine, right. So, now NH here, and this is nitrogen, and CH2 and Cl, that is it, right. So, now they are pretty, I mean now it is open, and once again the ring closes, okay, ring closes to expel this chlorine. Automatically chlorine minus will pick up this OH hydrogen of OH. So, eventually it will form this librium. Okay. So, what is the summary? So, that means this is and now many see think about this reaction was discovered 1960s. Even today people are working on these diazepines, simply because they want to look for more and more medicines. I mean, see, each individual will have different kinds of these symptoms or different problems. Okay. For example, I know this Alprazolam is almost now routinely used by many elderly people. If you are suffering from insomnia, what is that? Insomnia, right. Okay. If you do not have enough sleep, so you can just take one Alprazolam, not too many though. If you take too many, you are gone. Okay. You have to be very careful. No, not I mean, you will not be gone, but at least for a day you will have a nice sleep. Okay. So, but chemistry wise, what is the summary? Chemistry wise, what is the summary? That okay, we have covered achmatoic, Pian cartelli, Dimroth, Cornford, Steglich, all these. There is also one more reaction I did not talk about it, that Kronovsky or Boeckel height rearrangements, that also involves. I think just if you have a minute, we can just talk about it. I think we should know about it though, because again this relates to these enoxides. Enoxides, I think many of you probably know. If you begin with this, then trifluoroacetic anhydride probably, or just trifluoroacetic anhydride or trifluoroacetic acid maybe. It could be okay. I think any kind of anhydrides, right? Somehow it is missing. How come it is missing? Okay, it is okay. Trifluoroacetic anhydride, perfect chloride. So, what you will be getting? You will be getting this pyridine nucleus now, and the side chain is now functionalized. Side chain is functionalized, and you will be getting this OH here, or more precisely, if you will get this. For example, if you have a system like this, plus minus this thing that thing, and you have, let us say you have a groups here, and if you do the similar treatment, what you will find, the central ring would be pyridine, but only this ortho substituent will be converted to the hydroxy here, and mechanistically actually it first acetic anhydride first attacks this oxygen here, and then so I think you will be getting let us say something like this, right, because acetic anhydride, trifluoroacetic anhydride is basically equivalent to this one. So, it will it is a plus 1. So, we will get this, then hydrogen is eliminated. So, carbon double bond is produced, then the trifluoroacetic acetate, this one, it goes to displace this acetate, right. And then of course, then once you have a trifluoroacetic acid, and if you just water, that would hydrolyze the acetate to this alcohol. This is pretty common reactions. So, that means there is a good number of the rearrangements which are based on these reactions, and this is known as Boeckel-Hyde reactions. Sometimes people say Polonovsky reactions or Polonovsky rearrangement, and Polonovsky rearrangements. Okay. So, what is the summary? Heterocyclic rearrangement. Heterocyclic rearrangement, most cases, right, most cases they belong to the ring opening and ring closing, which are not ring opening, ring closing. Let us see, Akhmatovic, ring opening, ring closing, right, and Pian catalyst, that is also ring opening, ring closing. Dimroth, ring opening, ring